And when we go to the next speaker, it's Katarina Morovska from KTH that will talk about transformer.
Great. Hello, everyone. My name is Katarina Morozowska, and I am a postdoctoral researcher at KTH. During my PhD, I was working on dynamic rating and its benefits in terms of integration of wind power to the grid. And today I'm gonna talk about how resizing transformers can help to achieve cheaper and cleaner green electricity and also faster grid connection. And I'm also gonna speak a little bit about our future plans. So what is transformer? So most of you probably see these huge black boxes at the substation, which you don't really care about. But in fact, it's has usually a lot of extra capacity since it's a very over-designed unit, as our case studies show, and it has a lot of potential to help to integrate more wind power to the grid and reduce wind electricity price. What we'll speak of is dynamic transformer rating. It's based on using information from the transformer specification, also ambient parameters such as weather, ambient temperature and wind speed, and load parameters in order to figure out what is capacity limit of the power component at each time step. It's all based on the hotspot temperature, which is determined by running thermal models for transformer insulation. Normally you would like to keep it at around 110 degrees Celsius in order to make sure that you don't exceed your projected lifetime. Why do you want to do dynamic transformer rating? It's a very expensive component, and it usually takes a big part of capital investment, also operation maintenance. Usually they're over designed to a significant extent, and you could use them more efficiently, which would result in lesser material spendings, lesser usage of resources, and in the case of offshore wind farms, you could significantly save on the supporting structure. You could, if you would speak about the already existing units, you could potentially expand your wind parks by using the same grid, the same substation, and you could get cheaper grid connection. What we did with dynamic transformer rating, we used our first study several years ago. We used a transformer which was connected to the wind farm, and we analyzed its performance. So we had the yearly load and temperature data, temperature from the transformer oil, and as well as ambient temperature data provided by the Swedish DSO. And after thorough calculations with the help of our partners at ABB, we determined that insulation life expectancy is very high, almost 20,000 years. I have to state it's insulation, so obviously the mechanical parts would probably degrade faster, but it still is a clear identification that it's very over-designed, and it doesn't lose enough lifetime per day in order to justify such a large size. So we looked into two ways to use this. First is to increase the load, and the second is to decrease the size. So when we decrease the size of transformer from 19.4 MVA to 16 MVA, you could save around 1 million kroner approximately, but your installation lifetime expectancy is still very large. So you could potentially save a lot on investment. But if you plan future wind farms, but at the same time, you still have very high safety of your operation. Yeah, and I have to mention that there is slight increase in the losses. However, it's probably it's way less than the gain, the monetary gain that we could get. And another way is to use already existing one to potentially expand the wind farm. So we studied like different load increase factors, 10, 20, 30%, or here it's in per unit. And basically try to plot it against the loss of life or days per year. Like in principle, this wind farm, which this transformer was serving, could be increased up to 30%, and while still using the same unit. But yeah, of course, like it's not statistically correct to make generalization on only one component. So we got data on 9 more. All of them connected to wind farms, all of them in Sweden. This time we tried to experiment with hotspot temperatures, and we try to see how would you like wear off the unit like as much as you can. So we try to increase wind farms so they would like operate, so the transformer would operate at its rated power. And yeah, I have to mention like the data that we get, we were able to determine this relative aging rate, and it's very low for all of them. It's never more than 10%, while like if you plan a transformer to be operational for 50 years, then if the aging rate is 100, then in 100 years you expect it to be the lifetime to end. But with this aging rate, I don't know how many years it should operate. So after the load increase, we still had a lot of lifetime left. So what this information on all of those units that we studied could be used for could help us lower electricity price by investing in cheaper transformers and maybe operating the ones that we have more efficiently. And in order to do so, we need better planning. Here we saw an opportunity, and this is the work that we plan to do from now on with 2 other projects. So we want to use tools that wind planners have, wind farm planners have on wind resource and production of future wind parks, to also size transformers and size the substations which supply those wind parks. And basically this way you could have like this interdisciplinary collaboration between weather resource part and part from the electrical system, which would help to achieve better design and planning of wind farms in terms of electrical connection. And if we plan wind farms with smaller transformers, we not only reduce needed investment, we usually have more understanding of the component, and we could argue that by having this additional understanding and by maybe monitoring what is happening with your component, you can somehow increase their reliability because you will be more knowledgeable in making your decisions, and we could help to decrease the price of wind electricity. So we um, got a new PhD project starting in September. We got funding from WindL from the Energiemyndigheten, and it's a collaboration between KTH and Uppsala University with a group of Stefan Ivanel and also Hitachi ABB Power Grids and Vattenfall Wind. It's a project under the Stand Up for Wind framework, and we hope to get some interesting results within a year. And also, I'm gonna continue on working on studying more substation equipment like underground cables and using them for large-scale integration of renewables. Thank you, and yeah, if you have more questions, you can contact me using my email. Thank you.
Okay, thank you. Do we have questions for Katarina? We have what kind of transformer failures to expect?
I mean, if you overload your transformer, like above your hotspot temperature limits, then you can, of course, you are in a higher risk of the electric breakdown. But that could happen to any unit that you overload. It's just dynamic transformer rating allows you to operate it in like more dynamically and have like real-time knowledge on its actual capacity.
Yeah, we got a follow-up there. In case of failure due to underdimensioning of a transformer, what are the consequences, technical, economical, etc.?
Well, I mean, it depends. Like if it's a failure that results in damage of the component, then you will need to replace it. But I would say that like the our research is aimed at looking into ways to like have real time understanding of the operation and like sort of real time control. So to prevent this from happening, so we try to understand how the component operates and understand what are the hotspot temperature limits and how the like different loading patterns affect the aging to prevent that from happening. But basically, if you can keep your hotspot temperature below 110 degrees Celsius, then you are safe from those issues.
Okay, thank you. Are there aerodynamic transformer rating used somewhere in the Swedish grid today?
No, not in the Swedish grid, but I work with the National Grid US. They are starting. They already have a pilot project for dynamic transformer rating, but for now it's only used as a like protection and reliability measure to help the contingencies. But that's usually the first step. So like you start small and like it's too early to talk about planning with the industry, I think, because it's very risky. And there is not enough knowledge about it yet, unfortunately. But I think these like pilot studies, at least like trying to operate transformers for some time with dynamic rating in terms of like contingency help. I think that's first steps, and I'm looking forward to see the results from that pilot.
Yeah, sounds interesting. Any more questions? Okay, then we go on to the next speaker. Thank you, Katarina. So the last presentations will be with Emil Hillberg from RISE.
Yes, hello. Thank you very much, Sara. Um, all right, so my name is Emil Hillberg, and I'm with the RISE Research Institute of Sweden, and will be presenting to you today about the A&M for All project. Yeah, my agenda looks like this. I will talk a little bit about the project as such, and I will describe to you what A&M stands for. I will talk a little bit about business models for A&M and illustrate the toolbox that we will develop in this project and mention also demonstration sites. So the A&M for All project is funded through the ERANET Smart Energy Systems and is coordinated by me at RISE. And we are working together with these companies where we have Lund University, and we can mention Professor Olof Samuelsson and the PhD candidate Martin Lundberg there. And we have also Borgholms kommun present as a Swedish partner, and E.ON Eldistribution in Sweden. In Germany, we have also E.ON Solutions and RWTH Aachen University, together with the Luminasa. And we have also E.ON as a DSO in Hungary as a partner in this project. So the background to this project is that alternatives to traditional network expansions are needed to ensure a sustainable power grid development. And there are arising many new technologies and methods and different markets which are enables to us to provide an increase use in flexibility related to consumption, generation, and to the transfer capacity in the network. So the A&M for All project will develop solutions enabling an increased amount of renewables in the system with increased agility that is required from the developments on the demand and production sites. So the research, development, and innovation activities in this project are focusing on development of active network management methods, developing models for business to provide decision support for the market players, and in the development of an integrated toolbox for planning and operation. So the program has been ongoing for almost 1 year now and will continue for 2 more years. So what is A&M? Yeah, A&M is short for Active Network Management, and this is an expression used for exploitation of flexible network assets as a mean to provide secure increase in grid utilization. A&M provides alternative ways to address the needs in distribution grids compared with the conventional grid reinforcements. So in this sense, A&M utilizes advanced control systems and increased monitoring and communication to provide this. And here we are mentioning flexible network assets, and this is the intention here is to be able to control different kind of assets in the grid to provide this kind of flexibility. And here we're talking about loads, but also production as well as other controllable equipments in the system, such as capacitor reactor banks or tap changers or others. So the intention is that we are increasing the grid utilization, but it has to be done in a secure way. So here we need to consider the different limitations the grid has. And our focus is on the transfer capacity between generation and demand, where we have limitations on the physical capacity related to the thermal limits, as we just heard from a previous speaker on transformers, but it can also be on stability. And we have standard requirements relating to the power quality, and here our focus is on the amplitude of voltage. And furthermore, we have protective devices in the system which are needed to be considered in this kind of development. So an explanation of our focus is that the grid utilization limitations can be seen from two perspectives. The bottom-up perspective, let's say, that where we have the ampacity limitations in the grid, which relates to heating, as we just heard. It can be many components that can be a limiting factor in this system. But the summing up of currents from distributed resources, in a sense, resulting in limitations that can be identified in different places in the grid, coming from the bottom up, let's say. And here, on a very generalized level, we can say that wind power plants, main limitation is related to this, the ampacity in the grid. But on the other hand, we have also the voltage, and this is more of a top-down limitation, where voltage levels on the higher level in the grid are affecting downwards in the grid. And when we have production units in the low voltage grids, the voltage profiles which we see in the distribution grids are going in an opposite way than what they normally do in a grid where we have normally loaded. So this is something, the voltage rise here is relating much to the resistivity of lines and cables. And we're seeing this as one of the main limiting factors regarding solar installations on the lower grid voltage levels. From a business side of view, A&M solutions can create value by replacing or deferring traditional network expansion measures. We can, in this sense, not having to invest in large traditional expansions or shifting these further ahead in time. The other point is to allow a faster connection, not limited on the lengthy processes that can take to build new overhead lines, for example. And it's also decreasing the risk of ending up with stranded assets in a very uncertainties in the future where we are not certain about what kind of loading the grid will have. So in this sense, business models are needed for both the planning perspective and for the operational time frame. And on a planning perspective, we will look at how cost-benefit analysis can be used to address the viability of A&M solutions from an economic perspective. And this kind of analysis are highly case specific and have large influences from regulation and the future scenarios. And here we see an interesting fact that we are three European countries where regulation differs. So this will be a point where A&M can, where an A&M solution can differ from the economic viability perspective due to regulatory aspects. On the operational side, we will look into different kind of market models where we are differentiating between demand side management, where the flexible assets are directly controlled by network operator, and demand response, where we have a flexibility market and this is procured directly at the market. In the operational perspective, one also have to be aware of something economics relate to as a hold-up problem, relating to the maximum willingness to pay in an operational perspective can be very high. And if we have an incomplete contracting level, this can relate to significant increase in short-term dependencies between the network owner and the flexibility provider. In the A&M for All project, we will develop a toolbox where part of this toolbox will be used for supporting planning. So providing alternative planning solutions instead of the traditional network expansions. Looking at technical solutions and economical viability. And from the operational perspective, we will have an operational tool where we are integrating field devices, monitoring certain buses, and being able to control flexible assets, where the operator then can choose to utilize this flexibility to increase the possible transfer of renewables in the grid. These toolboxes and the developed A&M business solutions are going to be demonstrated. They will be demonstrated on Öland in Sweden, where the need is to be able to increase the amount of wind power generation in the grid. Where here we have the challenge with the ampacity of the overhead lines. And this will also be demonstrated in Hungary, where we have the different challenge relating to the voltage levels in the lower voltage grids and the penetration of distributed solar power. So yeah, that was everything for me. Thank you very much.
Okay, thank you. Do we have questions for Emil? Please write in the chat. I can start with these two demonstration sites. Will it be not looking at wind and solar in both countries? Now it looks like you were going to demonstrate the PV part in Hungary and the wind part in Sweden.
This will not explicitly be like that. I mean, we will demonstrate what is possible, and on Öland we have a lot of wind power, and the main challenge is there. But if we have the possibility to illustrate also the PV issue on Öland, this will be the case.
Okay. So, but no wind in Hungary.
This is not decided. It will be 1 year from now. The demonstrators will be on, but most likely it will be mainly PV in Hungary.
Okay. Okay. Any more questions for Emil?